Okay, so let's take a look at our data. This is how I organize my data. I had trial numbers, and the trial numbers run from 1 through 25. This is not exactly included in any calculations, just for organizational purposes. So every 5 trials belong to the same experimental setup. For example, I had 5 clips hanging. I basically did the backward hanging 5 clips and then hanging 4 clips with one on the glider, then straight clips with two on the glider, and so on and so forth. So these are the number of hanging clips. And then the next column, 2 columns came from the the photo gates. There's photo gate 1, photo gate 2. They both report centimeters per second values, and make sure you display your trailing zeros, right? And because we need acceleration in meters per second squared, I created 2 more columns of V1, V2s in meters per second, and it was a simple calculation, the centimeter per second over 100, and I will do the same over here, this other column divided by 100. So once I have this formula, I can just pull it to the right and then double click, let it go all the way down, because that is how you do it. This is not column C over 100. This is actually 2 columns to the left over 100. So if you autofill the formula to this cell, 2 columns to its left is the right E2. So now I have all of these, I can calculate the acceleration using this formula. I don't really discuss this in lecture, but I did have this in the lab. So the final velocity squared minus initial velocity squared over twice the distance traveled. Because we kept the photo gates at 50 centimeters apart or 0.5 meters apart, that times 2 is exactly a numerical 1. So in my formulas, if I use meters per second for speeds, I just need to do final speed squared or v2 squared, then minus v1 squared without dividing, because the distance times 2 is 1 meter, right? So that's how I did it. I took v2, the blue squared, minus the v1 red squared, and then I autofilled the rest of the A's. And for every 5 A's, these are supposed to be exactly the same setup. I did an average on the 5, and I had 5 different averages, right? And then for the forces, these are the forces acting on the whole, complete system, the system of the glider and all the clips. So the force is supposed to be this, and the number of clips, m, the mass of each single clip, and then times gravity. So the way that I calculated was this. I had a number of clips from this column, and I also have the total number of total clips, 5 clips. I weighed them, um, and I divided by 5. So this is the mass of 1 clip, and this is the number of clips, and that's 9.8. So it's a force. It's a small force, and that changes with the number of clips. So I'm using this column, number of clips, in my calculation. So I got basically pairs of data, force versus acceleration, another pair. There are 5 pairs, and these 5 pairs are what I would call sparse data or sparse arrays. So of course I can plot them, but I need to use LINEST, and the LINEST doesn't like sparse data at all. So I need to consolidate these numbers, which I did on the bottom right corner here. So what I did was I just copy pasted. I didn't do anything special, such as letting that equal to this. You could do that, but as long as you have all these 5 numbers, the forces, without spacing in between, and their corresponding average acceleration, that's all I needed. And we're going to plot the forces against accelerations. So it's probably better if you had the forces on the right side, so that you can select them both, and the axis will be correct. But if you had something like I did, the forces on the left side, then I had to be pretty specific how I was plotting. So let's see, I had the y-axis with the given with these. So basically I was plotting with these, although I was fitting with those. So I could change them. For example, I could change, see if I can move that around the force in the y direction. Okay, I can. Just have to resize that a little. Probably should resize before I move. And move the acceleration over here. It was the same thing. Okay, but this looks a little better since I was talking about using the consolidated data without the spaces, blank spaces. Okay, so one other thing to point out is the total mass of the system. And here's the mass of the glider, and here's the mass of the glider plus the 5 clips. So that's how I calculated it, just sum them up. And I also had a title for the chart, which I referred to. That's okay. This you don't have to do it. And these are equated to the column labels, or maybe those column labels are fine as well. And then I had a fit line, and there's a fit lines expression and R-square values. Apparently R-square values are pretty close to 1. That means lines are best describing what's going on. Okay, so let's scroll up a little. Scroll this up to the line list. So here's the line list output. I just had some labels around the output. So that is the slope, standard deviation slope, intercept, standard deviation intercept, and then if you look at the slope is supposed to be force over acceleration, which is in the unit of mass, right? Force F equals mass acceleration ma. So force over acceleration is mass. So that apparently is the total mass of the system, 673 grams. And if you go back up and look at how much mass I had, in actuality, I didn't have 673, so there was a little difference. And I would treat the slope as the answer that I obtained from experiments, because I did all the experiments in order to get a slope, right? And this direct measurement of mass as expected. I expect whatever I did here to be the same as the total mass. Apparently there's a little difference, right? So that's how you analyze the your data. So uncertainty over the slope, that gives you relative uncertainty. So it's 0.5%. It's pretty tight relative uncertainty, unfortunately. And then relative error is, let me scroll this down a little. Okay, relative error is the difference between the measured mass and the calculated slope mass divided by the measured mass. So we have 3% relative error, but we only have 0.5% of relative uncertainty. So because that is smaller than that, we couldn't prove Newton's second law, but we could at least say that we're 97% sure that the law is working. There might be some reasons for this. For example, the air track may not be level. Maybe some of the air holes are not really as good as the other air holes. There might be a little bit of friction we didn't account for. So the air track not level, maybe some small amount of additional friction, and also the string that we have that's pulling the glider. It may not be exactly horizontal. If it's exactly horizontal, then there's less issues. But anyway, so I had that calculated, so now I can make a conclusion. Although I couldn't prove Newton's second law, I'm still relatively satisfied with the only 3% of relative error. So back here, once again, this whole thing is the everything that I required, including the graph, the fitting with all the data. Thank you.